Good morning, everybody. My name is Joey Costa, and I guess this ties in with what we've been talking about how we make smaller devices. In my particular case here today is gyroscopes. We use these every day in our phones and our cars, but for what we need for NASA, it's a little more complicated. See if this works. Okay. Intelligent fiber optic systems. IFOS is a small company in Santa Clara. We're a C Corp. Been around officially since 2001. 8 of us, and 4 very, very keen consultants that have been with us for a while. Now, in general, fiber optics is prevalent everywhere, but in our case, we're looking at how to use it to keep an eye on very high-value things. And space exploration, I think, is a pretty high-value target. There are other things that are involved, of course. For example, Lockheed, this is what we're talking about today, fiber optic gyroscopes. But we also do things like a DTS, distributed temperature systems. And one of the customers was well ago. They do well monitoring and whatnot. The other one is a very good one. U of Calgary wanted to do a neuroarm project where they do brain surgery on you, but they had no idea what their forceps were doing. So if someone were to put a forceps into your head and it squeeze a little bit too hard, well, there goes your brains and your vessel. So they wanted a real-time feedback system. And so as a small company, this sounds really diverse, which is good. However, I found out that you almost need to know a little bit of everything in order to do something really well. So although we've been around for a while, we've been now slowly dabbling into the commercial, and that's going to increase hopefully quickly, I hope. Because that's where the opportunities really are. This is an eye chart, but bottom line is we have some interesting people that are sort of keeping an eye on us. Taher, the security expert, rely on every day on our computers, for example. The Bill Whitmore guy, he's a very high-level medical director that says what we can and cannot do and what we should and should not do in medical devices and stuff like that. Leonard Bond is the structural health monitoring expert. So we have a broad range. In particular, Ram is the gyro expert. So I would defer any questions to him. Today, I just want to clarify, it's more of the how and not the why, okay? We can debate the why all day. We'll go nowhere. But today, I just want to give you an overview of how we want to do something. It's a NASA-funded program. We started in 2011 with a very interesting concept. We went from CDs to DVDs to Blu-rays. So we said, well, let's go from infrared fogs to blue fogs. You get my point, right? And it'll be very obvious in a little bit why. So we were very lucky that NASA saw this as an opportunity to look at something different. And so in 2011, we pulled a T401, and they were kind enough to give us a chance. Now, again, the idea is to make them smaller. If you were to just do a Google search on fog technology, they are pretty heavy. I mean, they're big. And so when we went to visit our technical monitors way out in Wallops, they were saying, you can't fly heavy things like that. You just can't. So in concert with all the other presenters here that are looking at smaller and tighter technologies, we're doing the same thing. So one way to do that was to look at something they call the open loop architecture. Now, closed loop is, everybody knows it's good, it's got a feedback on it, you can do all kinds of stuff, but open loop is almost risky in the sense that, well, you don't know what's going on. You send a signal out, you hope it does what you think it will do. Well, there are ways to guide it with some firmware and whatnot, so that's a whole separate research area, but for now, we have some baseline to work with. And the trick here is to harness all the brand new, literally brand new, short wavelength technology. Infrared technology is what we use every day on our internet, cell phones, 1550 nanometers. Fiber optics in the visible, eyeball range, 500 nanometers, 600 nanometers, is very tough and also a very risky venture because everything from loss to scatter, dispersion, blah, 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 all the physics and homework problems we used to do, they really come back and bite us. So this is pretty clear. NASA needs some really small gyros for, as mentioned yesterday, maybe baby satellites, formations of them, and whatnot. So I guess our job, the bottom line, is to get all your projects to where they need to be and aim them appropriately, right? Like yesterday, someone mentioned the mirror was pointed the wrong way. Oh, that's a good example. The size limits are, well, pretty much a bowling ball, but a very heavy bowling ball, luckily. These are microsats, not nanosats yet. We haven't gotten it just yet. And of course, it has to survive the launch. One of the issues is you build something on the ground, you launch it, and then it doesn't work up there. That's no good. And the lifetime and radiation. Now, electronics are becoming more and more rad-hard by design, so I'm not going to beat that one a little bit. I think we can surpass that, like silicon on sapphire and stuff like that. Okay. But the optics is a whole new ballgame. We've had a very good run with Boeing, as a matter of fact. They were kind enough to let us use their facilities to test fiber optics in their, one of their radiation lab, Brell, up in Seattle. So we hit our materials very hard with one of their sources, and we found out that there was not much effect on it, which was good. So it shows that we can deploy in atmosphere and whatnot. And of course, just in general, just overall, you've got a pretty challenging thing to do. It's a very high-risk venture, and it has to last maybe from 6 months to 2 years. It has to survive all the orbital issues that you will face and whatnot. So it's not an easy proposition to satisfy. Apologize here. One more time. Okay. In the meantime, we've had some luck with several key people, Boeing. They actually, this is for real, they've actually called us, not just sending letters, they actually called us and knocked on our door. So we feel very fortunate. You know, again, very similar, the secondary launch, payload launching. Of course, Lockheed Martin always wants something for their ballistic missile systems and whatnot. Now, Infocon is a partner that we're working with in this project. They've already deployed on STS and ISS, so they're big boys. We're just kind of tagging along on their coattails almost. But their forte is electronics. So as I mentioned earlier, we do have an eye on how to solve that problem. And of course, with NASA, we are going to go after the phase 2 enhancements and whatnot, because after all, that's what this is all about. And there's a small little venture group in Florida who's always our little angel. They always help us find chunks of money, so when we're ready to commercialize, the funding is there, because everybody knows it's not cheap, and it's not easy to do that. Okay. A quick comparison. I'm not going to bore you with the details here, but there are all the typical ones, your MEMS and mechanical, and of course, the deployed fogs. Now, we are going after the big boys in a tongue-in-cheek sort of way. At the very bottom there, the Northrop Grumman system, the LN200, 200 meaning 200 meters of fiber, and I'll get to that in a minute, shows that they have a certain performance level, and those numbers are theirs. Our goal is to beat it, and I think we actually can do it. Now, I must apologize that because of the nature of this presentation, there are certain numbers I can't give, so I use very, very small or much, much less than, so you know what those mean. So it's an open loop fog, and I believe it's pretty advanced. It's a pretty one of a kind. And in general, like the LN200, NASA actually came to us and said, we like the LN200. It's great, but it's too big, it's too costly. And if something goes wrong, we lose a lot of money. They want something that's solid state. All of us do. So we took the all-fiber implementation, which means there's nothing dangling. Once you box it up, it's all inside. The only thing that comes out is maybe a wire and a fiber, which we can find ways to circumvent. The design for manufacturing DFM is very critical. I mean, just because we build one doesn't mean we can build a lot of them, so that's very critical. And of course, it has to be light and very tough and all that, right? So it's an engineering exercise now. That's why I said today is more of the how. Try that again. There you go. So we went with Gen 1, a pretty big cylinder, almost 3 by 2. And then, of course, we also have to look at how do we do the engineering tricks to make them smaller. As of today, we have built Gen 3. just got notice from 2 days ago that we actually fabricated, completed it. So it's now undergoing tests. So here's a basic diagram of what it is. We start with a source. It goes into a bunch of optics, but the bottom line is it goes into this fiber coil. So anywhere from 200 meters to a kilometer to 1.5 kilometer. If you go back to some homework problems, you'll notice that essentially it's a circle. You've got two photons going in opposite directions. They interfere, they talk to each other. When you rotate that coil, you get an inertial reference change, and so the photons give you some information. That information translates back into the gyroscopic effect, and we demodulate it out to get that information. So that's what that's all about. Now, the complication, though, is that modulator over there. You can't just build a coil, throw it up there, and hope to God to get some information. So you inject, this is kind of like an FM radio, really, right? You put audio on carriers and you demodulate, get it out. So it's kind of like that. We chose a piezo electric modulator because of many, many factors, but a few of them are up there in the sense that it doesn't care about space, and it's very low power. It's also very repeatable, very repeatable. And you know this because all of us as technologists and engineers, we use piezo drivers for very small movements, right? Nanometers of movements, sometimes picometers. And of course we use small diameter, very state-of-the-art fiber and blah, blah, blah. Okay. So here's an example of, this is Gen 1. It's very bulky, it's very big, but that was our first forte into it. We broke a lot of them, but we managed to make it. And actually, these are the ones that went to Lockheed. When Lockheed said, we want to buy 3 of them from you, we want to beat them up, and then we want to come back and tell you how good or how bad they are. Well, those are the ones they actually beat up. And they were very happy with it in the sense that it survived the test. We are still using them in our lab as of today. It's our workhorse. In other words, this is our reference. And the numbers are actually very, very good on this one. But we still have to make it smaller. So that's just a quickie overview of a one-axis system that we built, which is the first one. And then we expanded it to 3 because that's XYZ. And a very typical electronic board. Nothing fancy, but it is very big. That's like 4 by 5. It's huge. Okay. So a bit of an eye chart on the lower right, but what I'm trying to get across here is we do a lot of mathematics to pull the information out. And we found out that the noise, the random walk, is very small. The bias stability is actually very good. So the Air Force wants this example to point their pedestals and whatnot. NASA uses this to point at Mars. That's what they want to do. So it's very stable. All the accolades that we were hoping for actually came out. So we were very, very lucky, extremely lucky. Now, one interesting thing about this fog is the data rate. I mean, I can't say the higher end, but 40K is a very high data rate for gyros. And that's why this open loop technology is so good. It allows you to just go at full bandwidth. So whatever I modulate at, I can pull my information out at that same rate. Then we went to the Gen 2. So again, it's a lot smaller than Gen 1. So I can tell you that right now. And upper right is an example of why. We started out with a modulator that was pretty big, like an inch across. And it said, nah, that ain't gonna cut it. So we went to a smaller one. And we had to ruggedize it. And of course, electronics boards. Now, again, as of 2 days ago, that small electronic board is actually functional now. We had a lot of problems. I'm sure any of us who have dabbled in electronics will know that you build something that never works the first time. It's noisy. You have hum everywhere. You have dropouts in your data. We went through that suffering period, and it's now working. It's very quiet, and it's very stable. Now, just a note about the modulator. It looks like a solid-state device, and it is. But at the macro level, it is stretching the fiber. And all of us know that when you stretch something, you change the internal properties of it. In this case, a piece of glass has a certain index of refraction. When you stretch it, you change it. So as fast as you can change it is as fast as that index of refraction will change. And because of that, the phase information of the photons change. And that's how we harness the information. So we built a 3-axis version of it. Again, it's a lot smaller than 40. But it's very lightweight. We did a lot of mechanical modeling of this box. This is a very, is a very misleading slide. It looks so simple. It's not. That took many man-months to do, as to why we machined it the way we did, to lighten it up, how to get the rigidity and all that. So we did all that. Not only did all the simulations, we actually shook it to make sure that the sim and what we built actually was the same. And it was. Okay, now, this is the key of the program. Why a different wavelength? The figure of merit is this sensitivity, and it's, length, coil diameter, and the light wavelength. Now, as you can see, if you make your wavelength smaller, your sensitivity just goes up, especially the fact that it's in the denominator. So it was a very obvious thing to do, except in 2011, when we sat down and said, let's do this, well, there was no fiber, no components, no nothing. I mean, we had red lasers and red sources. We could buy that, right? LED, Radio Shack. But there were no supporting devices. And so this was a very tough infrastructure problem that we had to surmount and hit. And I think we were pretty successful. So it's about 2.5 times better, which means what? You can make it smaller. In other words, if I had a metric of 1, and now all of a sudden I have a metric of 2.4, now I can start playing the game of trade-offs. So I can make it maybe a little bit smaller and still retain the same performance. That's the whole goal of this program. And this is just a bit of an eye chart, but it shows what our Gen 2 was able to do, which is already equal or better than what was available. And of course, in Gen 3, we're going to supersede that, and we already did. We're about to give some formal numbers in our final report to this project. So let's look at the components. These are visible wavelength superluminescent diodes, which is not a laser. It's more of an LED, because the bandwidths are like about 10 nanometers versus sub-nanometer. So of course, the first thing we have to do is characterize these. And because this is not really designed for this application, we had a bit of a headache, and we had to work with the vendors. I mean, everything from where the pins were to how the fiber comes out, they were looking at us like we were aliens, but we managed to work with several vendors. This is one of them, to develop the components. This is one of them, the source. The coil, it's about 1.3 meters long, and in the gyro world, they call this navigation grade. There are tactical grades and whatnot, i.e. how sensitive it is. And this one is pretty sensitive. We found out that the fiber was well behaved. Very little change in loss over temperature, which is the military environment, minus 50 to plus 80. It's a pretty big range. And so we were very happy with this. This was our very first coil. Polarizer. Well, in our daily lives, like our sunglasses, they're polarized, so that light bouncing off your hood doesn't glare you. So same technology here, except no one had one for the visible. So as part of our infrastructure development, we had to work with the vendors to do this, and also in-house, we had to develop this part of it before we could send it out. And studying polarization, anything beyond 100 to 1 is a very tough thing to do. And we need greater than 35 dB, which is more than 5,000 to 1. So the effort and understanding and problems are, very tough to deal with, but we managed to get there. We're about 35 to 40 dB now. Our target is actually 45 to 50, so we're almost there. Sorry. Okay. Splitters. Yesterday, someone mentioned a beam splitter. This is essentially that, except the beam splitters that we can buy, or fiber splitters, are again made for telecom, or the 15 nanometer. And we had to go back to square one. How do we develop it for a 650? In our case, it's 650. We got some very good results, very small change in loss, and the split ratio was very constant, because in an optical gyro, your performance is very limited to how well you control your specifications. Everything, every component. If the components are stable, your gyro is stable. If they're not, your gyro is very noisy. Okay. Now the depolarizer, it is something that takes polarization, which is very quantized. We know, right? It's either this way or this way, and we have to scramble it. Because if we take two photons and we throw them at each other, they will talk to each other. However, if they happen to be orthogonal, they won't. So in a coil, you don't want them to talk to each other because otherwise you get the interference effect, and then you have this humongous glaring piece of data on your detector that supersedes all the fine bits of information you're trying to read. So you have to put a depolarizer in there. And in this particular case, as you can see, it's very small. I mean, point something dB. So this is not the first one, of course. It took a lot of work to get, but the vendors and us internally are learning how to build these. Now, this is a bigger picture of that baby modulator. It's a piezoelectric fiber stretcher, as we call it. And to test it, here we go again, there was no infrastructure. When we said, let's go to the, say, the vendor A, and you said, wind this for us and test it, they go, fine. Well, we can't test it. We have no infrastructure for visible. So we had to do it ourselves. And we went through many routines of this and found out that we just built the gyro. It's the easiest way to test it because the gyro itself is an interferometer after all. And we found some good results. We found out where this resonance was, how we can detune it. We want to operate off resonance, of course. And it produced, the lucky thing was a very efficient drive. In the infrared counterparts, we had to drive it with 0.6 volts or something like that, 1.2, sorry. And in the visible, we found we only drove it half. Now, there's a lot of physics behind that, but our results are matching with what physics is saying, which is very good news. So, try that, okay. This is the Gen 3. This is no longer conceptual, we're building it. This is just a pretty picture. I cannot show you a picture of it because it's all over the bench right now, but when we're finished, it'll look something like this. Now, the tough part about this is that optical tray component subassembly. Everything else is relatively finite in size. That component subassembly is a tray of all the small things that go into the gyro, the polarizer and your splitter and whatnot. And when you pack a gyro so small, your fibers have to coil back. And, well, fibers have a certain limit. Some can be wrapped around your finger, but some cannot. The current technology of visible fibers is the latter. It can bend up to a point, but cannot be bent very tight. So we have to be very careful how we design this. And also, after we build it, when you shake it, you can snap it if you don't do it right. So it's a lot of mechanics, a lot. Okay, now the other side of the equation is our university partner. Sorry, try that one more time. Okay, University of Alabama at Huntsville, they're helping us develop a very unique sort of semi-active damping. And the trick is to have a spring, so it allows some vibration and attitude control, but to make it a little smarter. And again, piezos are a very good example of how to do that. And they decided to put piezoelectric rods. They're very teeny, 5-6 millimeters long, 0.5 millimeter in diameter. And they shoved it inside this little piece of rubber, essentially, visco. It's silicone goo, it's rubber. And so what you're doing, essentially, is by taking the passive nature of the viscoelastic, which it just squishes like a spring, and put something that changes its rigidity depending on what E field you apply on it. Now you have a pretty good semi-active damping system. And those 4 pictures up there are just representative of the first sample that we built. Okay, and this is the theory behind it, which pretty much says, in the lower right, it says it works. So we went through some shaking and we beat it up. They built a cube. It's about maybe a 1.5 centimeter square, just to prove the concept. Now we're building a bigger one because our gyro is a little bit bigger than that. But it's essentially a combination of a spring and a damper. That's all it is. Okay, so we're now completing the gyro. We're already completed, actually, as of today. The debugging is the toughest part. Building it, now we're getting very good at it, but the debugging is very tough. The prototyping is out the door. Now we have to test it and find out how it really performs. Now, to take this to the next level is not a trivial task. Although now we have the vendors trained, so to speak, and we have our own in-house SOPs, to look forward in time and say, okay, even if we had the money today, how do we move forward? Well, there's a lot of stuff to do. I mean, your bill of materials, your corrective action reports, right? All that stuff that go into a production cycle is not a trivial thing to do. So as far as freezing everything, well, we're there. We already know what we need. We know what the specs are. We know what the windows of error are. But now the funding, if it ever materializes, is non-trivial. Now, so just an ROM on it, P2E is about, I don't know, about 500K or so. But in reality, when you move to the next stage of developing the infrastructure, which is not cheap again, that's where this big chunk of money goes. And of course, you have to commercialize, you have to transition it, you have to work with production homes, component manufacturers and whatnot, because we're a small company, we can't do these in-house. And it's pretty obvious why you want to invest in this. If you didn't, you couldn't put this kind of accuracy in small satellites or small craft, right? That's a bottom line. So for us, it's a no-brainer, but we have to prove the technology, and that's what this program's all about. The application examples are clear. The balloons, your baby satellites. And the mortar people came to us one day. Again, they were knocking on our door, which is very, very interesting for us. They said, we want to launch some mortars, and we have some of these gyros, but they keep breaking. Can you do something about it? So when we show them our data, they go, that's it, we want this. Can you help us build some of these? But again, it's a size. They're very tight restrictions. And so they were actually willing to sacrifice some of the pointing, because it's a mortar. It's not like they want to hit a dime on a cross street. They want to just launch the thing. MWD, which is the oil industry, they have a problem with the Earth's feature, the magnetics of our Earth. It's screwing up the directionality. Our fiber optic system doesn't have that problem. We can also make them a lot smaller than what they are getting and survive. I mean, they're talking 200 Celsius and 20,000 PSI. The sensors that they have now, the moment they put it down, they have to drag it back up because it's dead. So there's a lot of keen interest in this technology. This is just a summary of what we can do because of the nature of the work we are ITAR compliant. And we're not that big, not that small, but as you can see, we're very busy. All my benches are full. I always wish I had more space. You must have some fundamental clean room to do some of the very final work, so we have that. And that's my name, my address, my big boss, Bizad. You any business contacts, call him. ifos.com is our website. And I'm done. Any questions? Thank you. Uh-oh, I'm in trouble now.
Yeah, I might have missed it, but what was the projected mass of your Gen 3 integrated system?
As of now, the number I can tell you is less than 0.4 pounds, but it's going to be much less than that. Uh-oh, another one.
What are your power requirements for this compared to the state of the art?
The numbers that I recall, 12 to 15 is out there. Ours is already at 9 to 12, so we're going to drop it to below 5 because NASA wants below 2 for a balloon project. It's very tough, but it can be done. Any other questions? Okay, thank you very much.